I'm Mani Khanuja, Principal Generative AI Specialist Solutions Architect at AWS and author of 2 books. Last time we drew the map and found that your request moves through 6 stages. Today I want to zoom right into that map because there's one thing on it that surprises almost everybody the first time they properly look at it. Here's the thing. When your system is slow, you reach for the GPU first, right? It's the expensive part, it's the part with the impressive spec sheet, so surely it must be the part that's costing you all that time. But an enormous stretch of the path your request actually takes never goes near a GPU at all. And in my experience, that's exactly where the latency nobody on your team budgeted for turns out to be hiding. So, where does it go instead? That's what we're doing today. We walk your whole path together, end to end, and I'll point at every single place I've watched time quietly disappear. Let's follow one of your requests properly this time, and I'm going to name every single hop that it makes on the way. It starts at your client, and the first thing it meets is your load balancer, which picks one of your replicas to hand it along to. Then your API server accepts it. Now that's a web server, it's speaking HTTP, it's parsing your JSON, it's validating the parameters you sent, and absolutely none of that is machine learning in any sense. Then your text gets tokenized, which just means turning your words into the integers your model actually consumes. That's ordinary CPU work, it's single-threaded in a lot of stacks, and for a long prompt, it is genuinely not free. Now it joins the scheduler's waiting queue, and that is where it sits until your engine has room to take it in. Then, and only then, does it reach the engine step loop, which is the part that finally touches the GPU you've been paying for. Your model produces its logits. A sampler picks the next token out of them, and then that token has to be turned back into text again by a detokenizer. And right at the very end, it streams back to your user, usually over server-sent events, one small chunk at a time until you're done. So count them with me. Load balancer, API server, tokenizer, queue, engine, sampler, detokenizer, stream. 8 hops. And exactly one of them is the GPU you were worrying about, right? So when somebody on your team says the model is slow, what they've actually measured is all 8 of those, added together, and then attributed to one of them. So here's a question I'd really like you to sit with for a second. If 7 of those 8 hops are just ordinary software, what happens on the day that your ordinary software is slow? It blocks the GPU. And the people who build these engines learned that one the hard way. So what did they actually do about it? vLLM wrote this up publicly back in January 2025, and it is still how the engine is built today. They split the whole thing into 2 separate operating system processes. There's an API server process, and that's the one doing your HTTP, your tokenizing, and your detokenizing. And then there's an engine core process, and that one does almost nothing except run the scheduler and your model. They talk to each other over a socket. So why would you go to all that trouble? Because when those two live together in a single process, ordinary Python work sat directly on the critical path, and your very expensive GPU sat there waiting for it to finish. And honestly, I think that's the single most useful thing in this entire episode. A world-class inference engine was redesigned, not to make the mathematics any faster at all, but purely to keep the housekeeping out of the way of the mathematics. Let's look inside that engine core for a moment, because the scheduler you'll find in there is far simpler than most people expect it to be. It keeps 2 collections, and honestly, that's really all. There's a running list, which is the requests it's actively working on right now. And there's a waiting queue, which is simply everything that hasn't gotten yet. And why does that matter to you today? Because the gap between those 2 collections is your queue time. And your queue time is the part of the wait that no model benchmark on Earth will ever tell you about. On every step, it decides who gets served and how much they get. And a scheduling decision there is literally a dictionary mapping a request ID to a number of tokens. That's genuinely it, right? Just how many tokens each of your requests is allowed this time round the loop. And that one dictionary is why there's no separate prefill phase and no separate decode phase in there anymore. Now we spend an entire module on that decision later, so I'm deliberately not unpacking it here. I just want you to have seen the shape of it once, because when we do get there, it will already feel like something you've met before. Right. So where does your time actually hide along this path? Let me give you the 5 I go looking for first, roughly in the order I check them. Tokenization. It's plain CPU work, and a genuinely long prompt can spend meaningful milliseconds in there before your GPU has seen a single thing. Then detokenization on the way back out, which happens for every token you generate. Each one is tiny, and you're doing it thousands of times. And tiny multiplied by thousands stops being tiny. HTTP and streaming. Every chunk you push out carries its own overhead, and if you're flushing once per token over a slow mobile connection, your user will absolutely feel that. Then two that catch people out completely. Python's garbage collector, which can pause your process at a genuinely inconvenient moment and leaves no trace whatsoever in your model metrics. And the global interpreter lock, where two pieces of Python that both want to run at once simply take turns instead of actually running together. Now, here's what I'd really like you to notice about that list. How many of those 5 show up in a model benchmark? Not one of them, right? Your benchmark measures your engine. Your users measure your whole path. Now, I want to be careful with you here because I've said vLLM several times now, and there's a very good chance you aren't running vLLM at all. So, does any of this actually transfer to what you've got? Yes, almost all of it does. TensorRT LLM sitting behind Triton has the same skeleton. So does SGLang. The names are different, the process boundaries sit in slightly different places, but the shape of the path is genuinely the same shape. There's a client. Something accepts and validates, something tokenizes, something queues, something runs your model, something streams it back to the person waiting. Same 6 jobs, right? Somebody just gave them different names and drew the process boundaries in a different place. And that is very nearly the whole difference between one serving stack and the next. So when you move between engines, please don't relearn the path from scratch. Learn where that particular engine chose to draw its boundaries and which work it decided to keep off the critical path, because that's the interesting part, and it is very often written down for you. So what do you actually do with any of this on Monday morning? One thing, and I'll admit upfront that it isn't glamorous. Instrument the hops. Put a timestamp on when the request arrived, another when tokenizing finished, another when it finally left the queue, another at your first token out, and one at the very end. Because until you've got those 5 numbers in front of you, every conversation your team has about latency is somebody's opinion, right? And opinions get expensive very quickly when there are GPUs involved. Most teams I work with can tell me their end-to-end latency straight away, and then almost nothing at all about its shape. You want the shape, because the shape is the thing that tells you where your fix actually goes. And without it, you're guessing with expensive hardware. Everything I've quoted today is linked below for you, and I genuinely recommend the vLLM version 1 write-up in particular. It's an engineering post about an architecture change, and it's unusually honest about why they made it, which is a good deal rarer than it ought to be. The paged attention paper is down there too, and we come back to that one properly in Module 5 when we get to how the memory is actually managed. Next time we take those 2 halves we keep mentioning, prefill and decode, and we finally treat them as the 2 genuinely different programs that they actually are. See you there.